next week? Well, next week we're going to have a spring break. Did you know that? Starting Monday, 23 of March till Saturday inclusively. There are no classes in our college at all. No face-to-face classes, no online or Zoom classes. You need to take a break, well-deserved break. So if someone tries to log into Zoom, please don't panic because I'm not going to be on Zoom. Just recall that the college is closed, even virtually. That's good to realize. Anyways, improper integrals. Make sure that you double check all my work because I think last time something happened with the last exercise. So just finish it up yourself. I think it'd be better if you, because I stopped at some stage and I think you should finish it up because that way you will get the answer. Anyways, maybe over spring break you can try to do that. So what I want to do is more of improper integral story, one with the issues that happen to be when you utilize the infinite portion of graph here with your left side was vertical asymptote. So please notice that you again had an issue taking the antiderivative because at 0 it was not defined. So what they advise is to cut it out at some particular fixed value, call it as b, and then turn it to the limit when b approaches to 0. When b starts to approach to 0, you should be able to take the limit. And first of all, you take antiderivative. So once you do it, you don't have integral any longer. But now you can take your your limit when b is approaching to 0, so it disappears. It'll be just 3/2, and that's it. So the way to not plug in 0 when you try to find the antiderivative, because that's the standard procedure in here. So I can just do the exercise. Let's do one exercise so we can see better what this is all about. So maybe I can try one here with, oh, here's 59, for example. Nice exercise. 59, it says, take the antiderivative of 0 to 1 integral of x to the power of -5, right? Dx. So when you do the antiderivative, you're going to end up with x to the power of -4 over 4 from 0 to 1. And then you will see there is an issue plugging in 0. This is actually 1 over 4x to the power of 4. And when I try to substitute 0, I'm going to get 1 over 0. That's the issue. That's why we don't want to use 0. We put some letter, and that letter will be sent to 0 when you take a limit of it. So that way you overcome the issue with 1 over 0, because you're going to have at the upper limit is 1/4, well, times 1 to the power of 4. It will disappear, and then the lower limit is going to be b to the power. And b is a fixed number that you send to 0, right? So the first piece has no issues because it's just a fixed number. So limit of 1/4 is 1/4. Now, how do I take the limit when b is approaching to 0? Well, looks like we divide 1 by small, which is big, so there's infinity. So this will be a negative infinity. So interesting observation would be to notice that if b is in denominator, looks like when you take a limit at 0, it's going to be always infinity. If it's b to the fourth power in denominator, or third or first power. So this is something that worth to realize, right? So when x is going to 0, 1/0 is 1/1 small, which is big. So it is infinity. And for that matter, probably it's a good idea to also say, since we have our limits of integration that start at 0 and end at 1, then we're on the right side from 0. So it'd be 1 over positive numbers, it is positive infinity, and with a minus sign, it is negative infinity. So just to be careful with plus sign, because we have a function 1 over x to the power of 5, so it's some type of hyperbolic behavior, right, here and here. And we're dealing with a standard picture of hyperbola, so region produced by our favorite y-axis and hyperbola. So the region is here. And please notice it's infinite from 0 to 1 on the bottom. So this function bounds it, and it extends infinitely up. I say, Alex, this area is not negative. Well, we're not looking for the area. We're taking the integral. Integral is not an area. It could be related to the area, but it is not area. That's, I think, good to realize. But you could relate it to area, but that's something a little bit different. So anyways, the exercises here, so you can again double check this over coming long spring break. So it's a good idea. And I think these problems are not very hard, right? Problems are pretty straightforward in terms of the integration. And just this limit added is all it is in here. Now, we're starting completely different story. We're starting to work with so-called sequences. Sequences that have an infinite many terms, so sometimes people say infinite sequences. So dot 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 means it just continues forever. So 1/2, 1/4, 1/8, and so forth. So you could say it's 1 over 2 to the power of n, right? Is my term in here. So we have 1 over 2 to the power of n, like 1/2 is 1 over 2 to the power of 1. And the next is 1/4, which is 1 over 2 to the power of 2. So if I write 1 over 2 to the power of n, the question will be, what about first one? Well, you can say it's either 1 over 2 to the power of 0 for the first one, and that way you will have your sequence that starts with a index 0 and then a1, which is here. and then A2. But it's not very popular to call it like that. They like to start with a to the power of 1, A1, not with A0. So for that matter, how do I treat my first term? So it looks like I need to write this as shifted by 1 to the left side, shifted by 1 to the smaller side, or subtract 1 from the power. So that's not going to be description then, but n minus 1. So when I have the term number 1, which is here, a1, that will be a to the power of 1 minus 1, a to the power of 0, to the power of 0, which is 1. So that'd be then correct. A1 and then A2 and so forth. So this way I will make a shift. And that's good to realize that sometimes you need to either add or subtract 1 from your index. Every once in a while, we're going to see it later. So that's worth to think about. So there's sequences of numbers, but there are a few little tricks to watch out. For example, E, how can I describe that sequence? Well, notice these are the odd numbers, 3, 5, 7, 9, so forth. So if I call it as 2n, either minus or plus 1. So if my first term is with index 1, so to get to 3, I need to add 1 for the top. And then for the bottom, looks like we keep adding 3, right? So we keep adding 3. The question is to what? Well, looks like if I start with number 4, right? So if I add 4 with 3, or maybe with 3n, right? So if I add 4 with 3, when I have a1, which is in denominator will be 4 plus 3, which is 7. So you need to check, make sure that it works. For a2, it's Alex, I have to do all that. Yeah, it's not very hard. Turns out it's a standard procedure. I know it is something new. So if you get 3 times 2, 6, and 4, that's going to be your denominator, 10. And what about numerator? Well, the numerator is your 2n plus 1. So if it's 2 times 1 plus 1 is going to be just 2, and 1 is 3, and indeed it's working. And then 2 times 2 for a index 2 plus 1, that's going to be 5, right? And it's working. And you can check a few more terms later. So the point is we are producing the so-called nth term formula, or sometimes people put it in braces. They say the sequence an, which is 2n plus 1 over 4 plus 3n. This is interesting, and this worth to think about, or actually not to think about, but to try to produce it yourself. I think I should have it here somewhere. D and E, they don't work it out. No. Oh, okay. So anyways, I think I will go to the end of the section because this is, I think, worth to have some time spent on to start to get used to this indices, because as I said, we're going to work with it from now on a lot. So for example, let's try one with a negative sign. Exercise number 3. So with a negative sign, notice that sign minus, when you raise it to the power of 1, it's going to be negative. But if you raise it to the power of 2, it's going to be positive, as well as if you raise it to any other even power. And that's interesting to realize. So in this group of exercises, they want you to list first 5 terms. So I prepare 1 and so forth. So now I have the expression where I need to put 1 instead of n. So the first term is 3. Then I put, oh, when you say, Alex, you're not doing exercise 1, 2, 3. Well, let me do 1 and then I'll do 3. So for the next, it's going to be 3 to the power of 2, right? Which is 3 squared, 9. Next is index is 3. So 3 cubed, which is 27. So you can probably right away see what those are, right? 81 and 243. So you can just keep multiplying 240. Keep multiplying by 3. So once you got an idea about first 5 terms, I think you got already everything you need. So this is like a backwards process. So they give you the formula and they want you to list those terms. But in the previous examples that I just did on the other page, I was given the terms and I had to observe and decide if there is a formula, and looks like there is a formula that's 3 to the power of n, the one they actually gave us. So anyways, exercise number 3 is analogous, so we now use the negative. So for the first one will be negative 1/4 raised to the power of 1. Right? So it's a1. So power of 1. So it's just minus 1/4. Minus 1. Okay, so next will be now raised to the power of 2. So that's going to be positive, right? So I'm going to have 4 squared as denominator, 16, and numerator is 1. So sign changed. And for the next one, which is going to be, it's now power of 2. For the next is power of 3. So now the sign is also going to be negative, right? So the sign alternates, people say. So it's going to be minus. And you just square. Now you cube your denominator. So 16, you have now 4 cubed, which is 64. And etc. So you could just produce some more terms. I guess at some stage you say to yourself, producing 5 terms or 10 terms is kind of waste of time. You just do the same thing, right? So you don't want to mess with this. So when you have the formula, sometimes people call it as a recurrent formula, well, then you are given this sequence. That's the point. You can produce any term. You can produce term number 1,000,000. You just use instead of that power of n 1,000,000. So having a formula is always a big deal. And sometimes it's a good idea to produce the formula. So let's say for exercise like 23, I see here, you need to decide how do you move from first term to the second term. You say, Alex, if I add 3, right, I will get to the next term. Does that work? Well, let's check it. Another 3, yes, 8, another 3, yes, 11. So with 2, to start, you add 3 so many times, so you added n times. And again, it may be n plus 1, n minus 1, so you always want to check and see if that works. Like for the first term is just 2, so I think it's interesting to notice one exercise. We have 23, so it's 2, 5. I just give myself a little room so I can make sure that I don't have to make it look not nice. So if I try to put it as 2 plus 3 times n, please notice that my n needs to be multiplied by since always we start with the first term with a index 1. But it's not going to be 2 plus 3 because that's already 5. So I need to multiply it by 1 less. So it's not by n, but n minus 1. You see, this is standard. We already encountered it in the previous exercise. So from n, sometimes you subtract 1, or sometimes you add 1. And that's the idea. So let's try one more. Let's try 27. See, it's a good idea to try to do these short and nice problems. Compared with integrations that we observed last time, it's definitely much nicer, right? So it looks like now in 27 we have sign alternating. So it will involve negative present there. So first thing I look at is numerator, and numerator is the same. It is always 3, and this is great. So I'm producing the nth term formula just like we did here. So I will write the upper 3, and then I need to divide this by a. It's 2, so various powers of 2, right? So like 2 to the power of n. So if I divide by 2 to the power of n again, it's going to be for the first term divided by 2, but we need to shift it by 1 to the left. So it looks like, again, we subtract 1 from the power, so that way a1 is not going to be here, but a1 needs to be 3 over 2 to the power of 2 minus 1, 2 to the power of 1 minus 1. So there'll be no denominator, or 0 power of 2, which is 1. So that's first thing. And then I need to have that minus for the second term. So how can I do that? Well, maybe I can try negative 2 to be raised to that power, if that's going to work, or I need to have some other procedures done. Well, if I take negative 2 and raise it to the power of 1 minus 1, that'd be 0 power. Yes, that works. And if I try to get that negative 2, better use parentheses, for the second term, so that's not a1, a1 is. For the second term, I need to have a minus sign, so it'll be 2 minus 1. So the odd power will get us what I need, the minus. So indeed, my nth term is produced. Now, I want you to notice that's not unique way to get the answer. So with you creating the nth term formula, you may have various other approaches. So some people like not to have negative with the numerator or denominator. They may have like a negative 1 to some power, which is making things a little bit simpler, I think. But negative inside makes it shorter. That's why I went for that. But sometimes people just multiply it by negative 1 and then see what power is it, n or n minus 1. So that's another thing. So anyways, looks like we start to get an idea how to produce the formula for the nth term, which is the main thing, I guess, big deal in here. And then the other piece is to find the limit, to see where this approaches to. Well, looks like if you have powers of numerator and denominator that are the same, they're going to be just quotient of leading coefficients. So that'd be 5. Right? So the nth term approaches to 5 in this case, and that's a limit of entire sequence. What did you just say? Well, I think it's a good idea to maybe graph, and that way you will get a better feeling. So it turns out in all of these exercises, they want you to find a limit of the nth term. So I think I need some room. So maybe I can just clean the mess. So just stop this sharing. So that's the fastest way to clean the mess. And then share this again. Okay. So if you have a sequence of numbers that we just decided approaches to 5, then point of story is that may just start to decrease, get closer and closer to 5 from the right side. And the limit, so we say the A index n will approach to that limit of nth term, which is 5. So that's say A1, then it's A2. So that's one of the examples when we can approach to some particular number. We can approach to it from above. Sometimes people say on the bigger side, or we can approach to the same limit from below. When you, again, depends on the formula for the nth term, so you can get closer and closer. That's another possibility from below, from negative side, right? They were called left and right limits, if you remember in Calc 1. Or sometimes to your limit, you will approach from both sides. So sometimes if you have a limit equal to 5, you may approach to it, say, start on the left, and then you jump on the other side, and then jump again, and then jump again. So you can jumping around, and you're getting closer, but from either side. Or you may jump twice, and then on the other side twice, and point of story might still be close, and get closer and closer, and your limit is again 5. So that's why we say the limit of your sequence is equal to 5. When n goes to infinity. So when your terms, you just keep on getting next, A1, A2, A3, A4, A5, A10, A1,000, A1,000,000, A1,000,000,000, right? So it's largest and largest and largest in approach to infinity. So from this perspective, they, I think, produced very interesting way to describe the whole process by using functions. So I think so if I just look at the picture, I think there's a nice picture here. Look at the picture with those sequences on the left margin in here. So notice that if you have a function 1/2 to the power of n, well, you may use 1/2 to the power of x to start. And 1/2 to the power of x is defined for every value of x, every real value of x, right? So just, you can see that it keeps going and going and going to 0, right? So because it's having horizontal asymptote 0, so that approaches to 0 when, so you want to make sure you say when it approaches to 0, because depends what happens with x. When x goes to infinity, so you take a limit when x approaches to infinity or all the way to the right. Then your values, see, At 1, you have 1. At 2, you have 1/2, right? At 3, you have 1/3, 1/4, and so forth. So your function is going to actually deal with the following sequence. So it's going to be A2, 1/2. A1 is 1 over 1. A3 will be 1/3. It's so-called harmonic sequence, 1/3. The next will be 1/4, and so forth for A4. See, the index is nicely related to the term. It's like 1 over n. So it's approaching to 0. Yes, Alex, yours is a little different. It's not 1 over n. Yeah, but they're just giving you example. So the idea of that example, of this example, is that you have a function 1 over x, for example, that goes to 0 when x is getting to the right, getting very large. So the sequence, which is a portion of this function, see, the key idea is a portion of this function, is also going to go to 0. So also going to keep getting closer and closer and closer to 0. Or the same thing with 1/2. So if you put 1/2 for the first, is going to be 1/2 to the power of 0, which is just 1. The second will be 1/2 to the power of 1 is 1/2. The next will be 1/4. Then next will be 1 over 2 to the power of 3, which is 1/8, right, and so forth. So this term's also gonna go to 0 again when x is approaching to infinity. Well, with sequences, x always approaches to infinity because we always keep going to the right. So that's kind of not needed part, but that's what they're using to relate again the graphs of functions, this red graph of function, with just single points of the sequence. And again, the key idea here excuse me. The key idea here is that if your function approaches to 0, y coordinates go here, then any portion of this function, so like sequence in this case of points, their coordinates also going to go to 0. And that's the something that enables us to relate functions with sequences, which we're not really going to do much. But it looks kind of nice, right? So that's why they relate it. And the reason they relate this is big for the future, utilizing the so-called abstract definitions of the function. So in other words, when you decide to take more mathematical classes, say real analysis or function analysis, you're not going to get any pictures because we can relate something to the pictures in case we're dealing with XY plane or something very nice, but continuous functions. But in those areas of mathematics, they don't deal with nice functions. You cannot graph them. So they need to be able to approach it just from formulas, in other words, abstract way. And that's why they give you this so-called epsilon delta definition here, which is not for the really calculus 1 or 2, but I just need to, I think, stress it here. So I think maybe I'll clean mess on the left side. It's right on the way. So you can see the epsilon, and there is no delta but n for the sequences. Depends on the instructor. Some instructors really like that to stress epsilon delta definitions. Some instructors deliberately skip it. Well, the reason for them to skip is because there are no exercises in the calculus classes that actually expect you to use it. So they just skip it. But the point of this definition of limit of sequence is that they don't give you any pictures. So they just write it abstract way how you can describe the approach of your terms of the sequence to the limit. Well, they call it as L. So how they can approach. So started at some point, looks like probably somewhere here. For the function, if you were to think of it as a function, it's some wiggly thing, probably. That's what they utilize when relate to what I just talked about. So at some point, probably starting at this point, because after that point, we never move away from this tube, which is epsilon wide. So there's epsilon. You say, why is it epsilon? Well, it's historically they like to make it with Greek letter epsilon. They could put some other letter A, but they like epsilon, so it's standard for all calculus classes. So if you be in that tube, which is epsilon wide to the either upper or lower border, so starting at some particular term m, so starting this term, all other terms, in fact, entire function will be within this tube, so nothing will be all of a sudden jumping outside of that tube. So that's how they describe it with inequalities. So they say starting for term n, for all larger than that particular term, it says m, capital M, isn't Mary. So starting at this particular m, maybe 1,000, maybe million, whatever, there's some term m. So all next terms of the sequence are going to be lying within the tube. So how to write it with inequalities? Well, the difference between the limit and the term, and they will write it like a subtracting limit L and the next term A index N is less than epsilon. That's what means it's within the epsilon tube. So translation of the picture into inequality. So that's worth to think about if you plan to do some more math, because that's something you're going to work with a lot. And again, it's totally abstract, so you can use it for four-dimensional, fifth-dimensional structures. So you don't really need this be in XY plane, and that's the point. So you totally working with various whatever dimension you can even think of. And that's why, since you cannot graph anything in 5 dimensions, right? Well, maximum we can do is 3 dimensions. And that's why we need some other ways to describe things. And, well, again, we don't use this in Calculus 1 class simply because we're dealing with nice 2-dimensional situations, X, Y. And then in Calc 3, we move to 3 dimensions. But still, we can make pictures in 3 dimensions, just like in 2 dimensions. So we don't need it. So that's why lots of times instructors simply disregard it. So anyways, I don't want to scare anybody. In fact, I think since we have spring break coming, so maybe I'll let you go do one more exercise and just let you go. And then we'll continue that after spring break, right? So just want you to recall the definition of a special limit number E. And again, since we related everything to functions, we can just graph functions. So that's, I guess, very big help, which is in the way of kind of cheating, because lots of times you are expected to do everything by hand. But since there is a technology available, and I'm sure that some students are definitely going to use it, without even telling me. So for me, it'd be not fair to the others to say, no, no, don't use technology, do it by hand, because there is no way I can check, right, what you're using. So that's why I allow everybody to use technology. And for that matter, I will show you how to use technology. So I'm going to type graphing calculator. So if you type in the search graphing calculator, it usually appears pretty soon, graphing calculator. So there is a free graphing, click something, slash I was supposed to, graphing calculator. And very first choice, Desmos. The old days we used to have those Texas Instruments or so-called TIs calculator that were over than $100 in price. But now we have completely free, let me clean the mess, free calculator available 24/7. You don't need to subscribe anything or give anybody your email address. So you just type in the search graphing calculator, and the Desmos is very good, I think. Well, it could be better, but it's free, so I don't want to get anything else since it's free. So I click, there is a little keyboard symbol here in the corner. That's how it's being used. And now I want to enter the function 1 plus 1 over x raised to the power of x. I'm not entering it correctly. I need to put 1. So skipped 1. 1 and raised to the power of x. That's a special, sometimes it's called second special limit. So when I put it squared, it is something which is here power. I think I put the power, right? Power of x, not true. Okay. So why did I call it? They try to get it here. Well, what happens to it when x goes to infinity? So whenever you're trying to find a limit, it's always important to know what happens with your variable x. And it turns out when x approaches to infinity, the limit of this function is number e. That's the second special limit in calculus. You know what e is, like 2.71, irrational number. Kind of friend of number pi. Whenever you have circular structures, volumes or circumferences with a circle, you always have pi involved, or with a sphere, or with whatever circular structure. And here you have this approaching to number e. Again, if you have considered the limit when your x goes to infinity. Because if x goes someplace else, it'd be something else, of course. But when x approaches to infinity, it turns out there is a horizontal asymptote that happens to be 2.7172 and so forth. So it's a special number. That's interesting to realize, and it is kind of visible from the picture. I say it's kind of, Alex, I don't really see it precisely. Yeah, you can zoom out. So just keep moving, and you will see it is really approaching to horizontal line, and that is y equals to e. And that's good to know, and that way you don't need to remember anything when they want you to take some limits here in the calculus textbook. You just put them in the calculator, your function, and if you be able to see what it is, of course, you cannot see e because that's the irrational number. It's 271, so how would you see it? If it was 2 or 3, then definitely you would see it right away, but it's something one needs to remember. So that's, and analogously, you can find from now on using your graphing calculator any limit. Like for example, here is the one. Example 4, use L'Hopital's rule, do lots of algebra, but what you can do is take a limit again. What's important is when x is sent to infinity of your function x squared divided by 2 to the power of x and plus 1, minus 1. So whatever you have here. So you relate this function to the sequence when n is 1, 2, 3, 4. So if I decide to graph using my favorite graphing calculator, so I go back to calculator, clear this mess, and then I'm going to enter on the top x squared, and on the bottom we have 2 to the power of x minus 1, right? 2 power of x. Don't look at what is being produced in intermediate steps because it might confuse some people. So you don't want to just enter your entire function. So now I make sure that the minus will be on the same level as 2 is, minus 1 like that. So it looks like we can see what happens when x approaches to infinity, right? You can see that this y, this function f of x, which is my expression here, is turning into what? 0, right? So the limit of that is 0. We see it from the graph. And what they do, they use L'Hopital's rule, so they take derivative of numerator, so that becomes 2x, and then take derivative again, it becomes x. And then they have to remember that derivative of denominator is 2 to the power of x, so that's 2 to the x times the ln of x, and then again, so it just takes times the ln of 2. And it takes a little time to write, but again, with a calculator, of course, it's much faster. And then since your function is approaching to 0, then if you take a single point at x equal to 1, and then x equal to 2, 3, and so forth, see there should be 20 of them in between. And then next, have y coordinates going down to 0. So that's why the limit is 0, not just for a function, but also for the sequence, right? So instead of x, if I put n, and n runs through integer, or actually only positive integers, or the natural, sorry, so just integer numbers, right? 1, 2, 3, 4, and so forth. So since the function that is bigger in infinitely many points on the grid goes to 0, then if I just select points from this graph, they will also have their y coordinates going to 0. So that's the key observation, and that's where we use graphs of functions or various algebraic things that we already learned because we worked a lot with functions. Now we transfer those tools to working with only parts of functions that are called sequences. So that's important to realize, and that takes a while to understand. So that's why I think we are having our break at the right moment. So we would probably, during the spring break, benefit from thinking about this section and maybe doing some exercises at the end. I did not go over everything which is in it. Maybe next time, which is going to be in about 2 weeks, right? We will return back to this story and we'll see some more interesting ideas. And for now, I guess I'm going to end it. I think you deserve to rest, so I'm going to stop this recording. Actually, yeah. I wanna stop this recording and thank you for being here and have a great break. Enjoy your spring break.